Okay, so in this video, we're going to talk about how to graph certain functions using transformations. So the idea is when you go to calculus, yes, there will be more complicated functions that you might need to use a graphing calculator for, or to use some calculus to help you graph. But there are certain functions that you should just be familiar with, and then any transformations from what we call a base or a parent graph. So I'm going to introduce 4 quote unquote base or parent graphs. These are what I mean by these are just the simplest versions of these types of graphs. So the first one is f of x equals the square root of x. If you just plot points, the smallest number you can take the square root of is 0, and the square root of that is 0, so it passes through the origin. And you can plug in points. Square root of 1 is 1, square root of 4 is 2, and so if you put those together, it kind of curves off. It's actually half of a sideways parabola. That's going to be one of our other graphs. But that's the graph of f of x equals the square root of x. The next one, f of x equals the absolute value of x. Many people are probably familiar with the classic V shape of this graph, which comes from just plugging in points, 1, 1, 2, 2, and then -1, 1, -2, 2. It has the same y values for each of the corresponding negative x values. So that graph has the bottom of its V at the origin. And then f of x equals x squared. That's a parabola. Again, probably a graph many of you have already worked with extensively, but just to remind you, the U shape of this graph has y-axis symmetry, just like absolute value of x. So that's a base graph. And then one more would be f of x equals x cubed, a cubic equation graph. If you plot some points, you'll see that this graph actually comes up. It does actually flatten right at the origin. It gets horizontal there and then curves up like this. So this is the graph of f of x equals x cubed. And so what we're going to do in this video then is practice with those 4 graphs some of these transformations that I mentioned. So first, let's start off with reflections. So any of these graphs, we can create another function by reflecting these graphs either about the x-axis or about the y-axis. Some of them you wouldn't notice any difference, right? If I take f of x equals x squared, if I reflect it, if I flip this over the y-axis, this over the y-axis, you're not going to notice any difference, right? It's the same thing. But certainly a graph like the square root of x, if you reflect that over the y-axis, that's a different graph. Same thing with the x-axis. Okay, so if we were to take y, if we were to replace our x with negative x in any function, that is going to have the effect of reflecting our function about the y-axis. And the reason that's true is you're essentially making all of your x values negative, right? You're taking these x values and you're making them negative over here. So that is going to reflect them about the y-axis. If you take f of x and apply a negative outside of the function, that's going to make your y values negative or opposite sign, which is going to, if you think about it, reflect your function about the x-axis. So let's see some examples of these reflections. So if I take y equals the square root of x and replace my x with negative x, maybe we can do this. Our old version of square root of x looks like this, if you recall. This is y equals square root of x. Passes through some points, 1, 1, 4, 2. But the idea now is I can now plug in -1 for x because I'm going to multiply that by negative and it's going to become +1. So instead of 1, 1, what I'm going to have is -1, 1. If I plug in -4 and then apply the extra negative, then that's going to come out to be 2. And so, yes, as discussed, you're going to get your parent graph essentially can be thought of as being reflected over the y-axis. Okay, what about, in this case, y equals negative x cubed? It's not with the x, right? If I had to put parentheses, it would look like this. there's x cubed, and then I'm applying the negative. So this would go under this category here where I have the negative outside. And so what that's going to do is reflect my y values. So I'm going to draw maybe like I did on the last one. Here is the graph of f of x equals x cubed. And all that's going to happen is this part is going to reflect around the x-axis. Now this part, which was negative, is going to reflect around the x-axis too and rise above the x-axis. So here we go. That's this graph right here. And all these, if you're not sure, you can still plug in points, right? For example, if I plug in 1 here and cube it and then apply the negative, it's going to be 1, -1 instead of 1, 1. If I plug in +2, I'm going to end up getting -8, right? So you can confirm this by just plugging in points, but it's helpful to spot the transformation so that you can construct the graph more quickly. Okay, so let's look at another one. Here I have y equals the square root of x, and I have the negative in both spots. So this is just to remind you, you can take a graph and apply both transformations. If this was my original graph of y equals square root of x, this negative is going to reflect it about the y-axis. So that would go like this. Here's, well, let's make it a little bit better. Here's y equals the square root of -x. And then if I apply the negative on the outside of that, that is going to reflect this graph around the x-axis. So this graph would look like that. Of course, it's just the blue graph here, right? Not those others. These were just showing the different transformations. Okay, so in addition to reflecting functions about axes, we also talk about translations. Translations are moving your graph up and or down. So if I have an equation and like f of x is our base graph, and I subtract something inside with the x values and then add something outside, one of the themes I guess I want you to come away with is anything that's done inside here is going to affect my x values because that's with the x, and anything outside is going to affect my y values. So the way it works is, as far as the x values, having x minus h actually moves your graph right, not left. A lot of times you would think it would be left, but it's actually going to move it to the right. And we can talk about why that's true in a minute. And then the plus k is going to move your graph up k units. So an example of that, y equals x minus 3 squared plus 1, your base graph, I'll just draw it kind of lightly or in red, is y equals x squared. And notice the bottom, the minimum value of x squared is 0, and that's because the smallest number you get out of this is if you plug in 0 for x, y is going to be 0. But this sheds some light into why x minus h moves the graph actually to the right and to the left instead of the left. Because notice what's the smallest thing I can get out of this is going to happen when x is +3. That'll give me 0 squared plus 1. So that's why this graph actually moves over 3, up 1. And it's a parabola, so it'll look. Remember, for a parabola, this bottom part we also call the vertex. Vertex. V-E-R-T-E-X. Okay, so it's moving it right 3, up 1. Okay, here's similar thing with the absolute value graph. So my base graph is just absolute value of x. Plus 4 is actually going to have the effect of moving my graph to the left 4. So it's opposite of what you would think. But for the y values, it is what you think. This is going to move my graph down 3. So instead of, maybe I'll just draw the actual graph this time. Instead of your base graph, absolute value of x, having its vertex essentially at the origin, we're going to move it left 4 and down 3. So it might be -4, -3. Now, one thing before I finish sketching this, I might want to check out some points here to make sure I have a really accurate graph, because I don't know if this thing is going to go like this, if it's going to cross up here. So an easy thing I could do is I could find my y-intercept, and I'll have a point to connect to. To find your y-intercept, when it crosses the y-axis, x is equal to 0. Set x equal to 0. So we can do that shorthand. We can do it a couple of ways. We could also say this is just the point when x is 0, and you just visually plug that in. X is 0, absolute value of 4 is 4, -3 gives me 1. The other way you could do it is if I called, okay, you know how oftentimes with y, you can also call that f of x. So the other way to explain how to find a x-intercept is you're really finding f of 0. You're finding the value of the function when x is 0, which is going to give you 1. So this point is 0, 1. My absolute value graph looks like this. We're going to do some other graphing problems in a minute here where we actually go ahead and find the x-intercepts as well. So we'll do that again. But let's look at the third way we can transform a function besides reflections and translations are stretches and compressions. And you can, when I say stretch, you can stretch the graph out vertically or horizontally. Compress means you're making it smaller in either the y or the x direction. And those can be spotted if you have an equation like y equals some number a times f of x. Notice that's outside, it's not with the x, so that is going to affect my y values, which means vertical, right? That's your y values. It's going to cause a vertical stretch. If a is greater than 1, but if a is a fraction between 0 and 1, like 1/2, then that's going to cause a compression. So if a is between 0 and 1, something less than 1, and that would be a compression. So here's a couple examples of that. And here, I guess I'm going to go back to drawing my base graph. So if this was y equals absolute value of x, and remember we had some points on there, 1, 1, 2, 2. Here, what's going to happen is you're plugging in the same x values, but now you're going to multiply your y values by 3. So instead of passing through 1, 1, it's going to pass through 1, 3. 2, 2 is going to pass through 2, 6. And you're going to get a much steeper, and it's going to be the same on the negative side too. So you can see it's kind of like stretching this graph vertically, pulling it upwards, pulling these points up. Whereas a graph like y equals 1/2 x squared, here's my regular graph of x squared. Now I'm taking these y values and taking half of the y values, right? I'm still plugging in the same numbers, squaring it, but then I'm taking half of it. So instead of passing through 1, 1, it's going to pass through 1, 1/2. Instead of 2, 4, it's going to pass through 2, 2. And the left side is going to look similar. So you can see it's, like we call that a compression. You're pushing down the y values, making it flatter. Okay, and then the last thing we can do is do the same thing, stretches and compressions, but horizontally with your x values. And the way you'll spot that is if you see y equals f of b times x, so some number times the x on the inside. Now, as we saw with the translations, where it was kind of the opposite in that x minus h, you'd want to say that that's going to move it to the left. Most people think negative, it would go to the left, but it actually went to the right. The same kind of thing is true with the compressions. You would like to think that to make it a horizontal stretch, you would want to use a big number, bigger than 1, but it's actually the opposite. You would need to use a fraction for b to stretch out your function horizontally. And if you want to do a compression, now you want your b to be greater than 1. That's going to shrink the graph. And it's easy to see why that works. if we use, say, y equals the absolute value of 3x, here's my base graph, 1, 1, 2, 2. So the way you could think of it is, we know the absolute value of 1 is 1, but what would you have to plug in for x to get the inside to be 1, right? You'd have to plug in 1/3. 3 times 1/3 would give you 1, right? So instead of passing through 1, 1, it's going to pass through 1/3, comma 1. See if I can sneak that in here. 1/3, 1. Instead of passing through 2, 2, 2 times 2/3 would give you 2 for x. So it's going to be 2/3, 2, 2/3, 2. Now it kind of looks, the thing with some of these, you could argue that that's a vertical stretch. It looks steeper, but it's really what's happening is it's getting squished in. That's a compression by a factor of 3. Now, if you try something like a fraction, then what's going to happen? Let's get our base graph. Let's call this 1, 1. Let's call this 4, 2. So in order to get 1 for the inside, what you would have to plug in for x now is 2. So instead of passing through 1, 1, it's going to be 2, 1. In order for this inside to be 4, you'd have to plug in 8. So then it's going to be 8, 2. Let's say that's like right here. And you can see what it's kind of doing is stretching out the graph horizontally, stretching out those x values. Okay, so actually that's everything that we do with transformations. You can reflect your graph, you can translate your graph, and then you can stretch or compress it, both vertically and horizontally. So now let's practice graphing, getting an accurate sketch with these transformations. And this time we will find intercepts as well as important points. And when I think of an important point, the base graph here is y equals x cubed. And remember, y equals x cubed, I'll just draw a little mini version of that, looked like this, where it got flat right at the origin. I would say that's kind of an important point where the graph flattens out. So where is that flat point going to be? Well, we can spot this -1 is actually moving my graph to the right 1 unit. The +8 is moving my graph up 8. So that means every point on this graph moves right 1 up 8, including this flat point. So it is now going to be at 1, 8. Let's say about right here. In my x cubed graph, I know what it looks like this, and then it kind of flattens out and then goes back up. We're also asked to find intercepts, both x and y-intercepts. So let's do that. My y-intercept, I just abbreviate INT, as we saw, is what happens when you plug in 0 for x. Most of the time you can do that in your head. If you plug in 0, -1 cubed is -1, plus 8 gives me 7. If I want to find my x-intercept, when my graph crosses the x-axis, it's not x that's 0, it's y that's 0. So to find your x-intercepts, what you always do is you set y equal to 0. Remember, f of x is just a fancy name for y. So we're setting y 0 equal to x minus 1 cubed plus 8. To solve that, we can move this over. You can take the cube root of both sides, because remember the cube root of -8, number times itself 3 times, that gives you -8 would be -2. And that just becomes x minus 1. And if I add that over, I end up getting -1 for x. Okay, let's look at this next one. F of x equals 8 minus 2x squared. And if you want to, you can even do things like this just to make it look a little maybe more natural this is the same thing as -2x squared plus 8, because usually we spot our vertical shift upward, right? As the number that's hanging out at the very end. So if I rewrote it like this, I can see that this is just the graph of y equals x squared moved up 8. The negative is outside the function. So remember, that's going to cause a reflection about the x-axis. And that too does cause, we saw that's a vertical stretch. Now, the thing with vertical stretches and compressions, and same thing with horizontal stretches and compressions, is it's in there, it's built in there, but oftentimes you don't really see it. The only time you'd really notice a vertical stretch, let me go back to my notes here, is, like if you look at these, if you graph them together with their base graph, you'll notice that one of them is flatter or one of them steeper, but they have the same shape, right? If somebody gave me this graph and I just drew something that looked like a U, how am I to know that that's y equals x squared or y equals 1/2 x squared, right? Unless you have something to compare it to. So you're not really going to notice so much the stretches. They do come out when you find things like intercepts, but you don't have to really think about them too much. Remember, my base graph looks like this. This is y equals x squared. We know it's going to be a reflection, so it's going to look this way. It's going to be an upside down parabola. Raised up 8. So let's just start with that. If it's raised up 8, the vertex is going to be at 0, 8. And it is an upside down parabola. So it'll look like that. Let's find these intercepts. We already found our y-intercept. That's the same thing as our vertex. So our x-intercept, if I set y equal to 0, I can move this 2x squared over, divide by 2, and then when I take the square root, both sides, remember to do plus or minus. So I get x is equal to plus or minus 2. Again, see how the vertical stretch is in there, right? It's affecting my intercepts, right? When I'm dividing by 2. Imagine if it wasn't there, right? Then I would have x equals plus or minus the square root of 8, which would have been a little bit further away here, right? So the vertical stretch is part of my function. It's just, again, it don't have to address it specifically most of the time. Okay, got 2 more here. Let's do one with an absolute value. 2 times the absolute value of x plus 3 minus 8. Let's identify the transformations. The minus 8 at the end is going to move my graph down 8. That's affecting my y values. The plus 3 is going to move my graph left 3. And this 2 outside my function, that is also a vertical stretch by a factor of 2. Again, like the last one, we're not going to notice that very much. So it's more about finding the bottom of the V. And then when you're doing the intercepts, the effect of that 2 will come out. So when this is 0, that's going to be left 3 and down 8. Left 3, let's just say that's right here. So that is the bottom of my V. Now let's find things like my y-intercept. If x is 0, absolute value of 3 is 3. 2 times 3 is 6. See, there's the effect of that 2. 6 minus 8 is negative 2. And my x-intercepts, setting y equal to 0, I can move the 8 over, divide both sides by 2. Oops. And remember, if you've got absolute value of stuff equals 4, there's 2 equations, either x plus 3 equals negative 4 or x plus 3 equals positive 4. So this gives me negative 7, this gives me 1, which makes sense. I should have 2 x-intercepts here. Let me draw this first. I'm going to call this point right here -7, 0. And then one more. Okay, f of x equals the square root of 4 minus x. This one's a little bit tricky. What you want to do is think of this graph, because usually when you see a translation left or right, it's usually the other way around. It's x minus 4 instead of 4 minus x. And so you do need to make it look like that. If you factor out a negative, this is the same thing. And then we can see that what we have is two things going on. This negative with the x is going to reflect my graph around the y-axis. And then we can see that it's actually been moved to the right 4 units. So now remember, a square root graph reflected around the y-axis, normally it bends off to the right, so it's going to bend off to the left and then get moved 4 units to the right. So 4, 0 is its starting point. And it's going to look like this. And we could easily find a y-intercept for that by just plugging in 0, and you end up with the square root of 4, which is 2. Okay. One note of caution on this one, for this kind of a reflection and transformation, notice it's not, you don't want to, don't translate and then reflect. Because you could mistakenly say, okay, I know this square root graph has moved over to the right. So you could say 4, 0, here's my square root graph. And if you then say reflect around the y-axis, you might mistakenly think that it's going to be over here, right? If you reflect that around the y-axis, you might think it's going to get reflected and look like this, when clearly that's not right. Of course, things like finding your y-intercept, right? If you thought this was the graph, then it wouldn't have had a y-intercept, but we can see it definitely does, right? You could argue, if you translated it over 4 units first, that instead of reflecting around the y-axis, what you're really doing is reflecting around the line x equals 4. And then you would have had the correct graph. But you don't want to translate and then reflect around the y-axis. That's going to give you the wrong graph. Okay, so just watch out for that. This is the correct graph. All right, hopefully this is helpful to help you graph functions from base or parent graphs using transformations.